Yeah. Okay. Good afternoon, everyone. Welcome to the second installment of the mini school on quantum thermodynamics. I don't need to introduce Graeme again because you saw him already in action last week, so we can keep this short and sweet. Yeah. So, Graeme, are you ready? Perfect. Okay, then now Graeme and I are sitting in the same room, so I will mute myself now and hand over to Graeme. And all of you know the rules of the game. If you have questions, please use the Q&A, and maybe at the end of the presentation you can raise your hand for real or virtual, and we can give you the opportunity to ask the question in person. We are not so many; we can do that easily. Okay, so let's start. Graeme, thank you very much.
Okay, just to check, you can hear me fine. Everybody can hear me fine. Yes. Okay, that's good. Yeah. Okay, cool. Yes, thank you. Thank you, Professor Cheney, for that kind introduction. So, without further ado, let me just share my screen. Hopefully, it should be the right. Is this? Yeah. Okay. Okay, and you can see my slides changing just to confirm. Okay, everything's good. Cool. Okay, yes. So so welcome back, everyone. So this is the second lecture in the NITheCS Mini-school series, Introduction to Quantum Thermodynamics and Open Systems Perspective. So in last week's lecture, I kind of gave a motivation to why hopefully quantum thermodynamics is an interesting and currently quite active field of research. And most of the content was devoted to kind of giving you a kind of background in basic kind of quantum mechanics and the kind of principles underpinning it. And so in this week's lecture, we'll kind of talk more about slightly more advanced material. So we'll go into looking at introducing the concept of Markovian master equations and how these can be used to derive within the Markovian framework the first and second laws of thermodynamics. So okay, let me just illustrate that in this slide. So yes, last week was mostly background. This week we will focus on the idea of Markovian master equations as tools in describing the dynamics of open quantum systems, so quantum systems are in contact with a thermal reservoir. And then we'll use this to if time permitting, hopefully use this to illustrate how we can formulate the first and second laws of thermodynamics. And obviously the content I gave here will be used in the following lectures. Okay, so just, before I start, actually, I should just point out that, so I think there were a few people last week asking if the lecture slides were available. So I just wanted to mention that if you go to the NITheCS website and look under the events page, where this mini school is listed, so where the link to the recording of last week's lecture is located, the lecture slides from last week should now be available in the same place. So if you have any trouble accessing these, then just then let us know. And I also plan on making these current lecture slides also available after the lecture. Okay, so just to briefly recap what we looked at last week. So we introduced the framework of open quantum systems. So essentially an open quantum system is some kind of arbitrary quantum system of interest which interacts with a macroscopic entity that we label the reservoir. So the starting point is that we treat an isolated system that itself is composed of two subsystems, so our quantum system and this reservoir. And this kind of bipartite situation, our quantum system is usually some kind of entity of interest, so it could be something that we're interested in measuring in experiment, whereas the reservoir is something macroscopic and it's something that we assume we only have very limited control over. And so in this kind of framework, what we can do is analyze how our quantum system of interest, how its behavior is affected by its interaction with this thermal reservoir. And so our starting point for this is to note that for a composite system, the corresponding state space can be constructed from the tensor product of the underlying state spaces. So here, S just represents our system and R represents the reservoir. And so if we introduce these two orthonormal bases, so here I use this kind of K Latin notation to indicate basis states of the system and the Greek notation to indicate basis states of the reservoir, then we can introduce what's called the so-called reduced density matrix. So this is an object that fulfills all the criteria of a density matrix. So it's a matrix which has unit trace, is positive and Hermitian, and we can generally construct this so-called reduced density matrix through a partial trace operation. So this so that you can think of formally as this kind of partial trace operation as a linear map from linear operators acting on the composite system reservoir space to just operators only acting on the open system space. And so generally this partial trace can be performed with respect to the basis states of the reservoir. So we say in this equation, we say that we're taking the partial trace over the degrees of freedom of the reservoir to obtain the reduced density matrix of the system. And in general, you can show that just using the general expression for the state of a composite system, which I gave in last week's lecture, you can generally write the reduced density matrix of our system in the following form. And provided that the density matrix for the composite system reservoir space is normalized such that its trace is 1, then we can show that the reduced density matrix equally has trace 1. And similarly with the other aspects of the density matrix rho, like for example, the fact that it's positive and Hermitian also carries over in the same way to the reduced density matrix. And so in that regard, it represents our reduced density matrix rho S represents a possible physical state that our system can be in. So another way of expressing this is to say that this object rho S encodes all measurable information about the system. And so there's formal ways of showing this based on demonstrating that the measurement of any local observable system can be obtained by measuring its expectation value with respect to the state of the full system reservoir, or equally just with respect to the reduced density matrix of the system. So this is kind of formalized in these two sources. So this archive paper, archive notes of LIDAR, and also the book of Heinz-Peter Borio and Francesco Piccioni. Okay, so when after we looked at the density or the reduced density matrix, we conceptualized time evolution. So how do we describe the time evolution of an open system that's in contact with a reservoir? So we do this through starting with assuming our composite system is isolated. Its time evolution is unitary as prescribed through the Liouville von Neumann equation. And so we can construct our reduced density matrix, which is a time-dependent function, in the following way. So we just evolve our composite system unitarily through this unitary time evolution operator, and then we take the partial trace. And we showed that under this, under a so-called separability condition, i.e. that the density matrix of the composite system plus reservoir is initially factorized, then we can write, we can construct this expression can be equivalently written in so-called Krauss representation. So this depends on the so-called Krauss operators. So these are just kind of, generally they're just bounded operators of our system. And the way that we can show this is by using the so-called spectral decomposition of the reduced density matrix of our reservoir. Okay, so yeah, as I said, so this construction it relies on this so-called separability condition. So this kind of assumption maybe seem, physically may seem somewhat unclear, but essentially what we're saying here is that our system and reservoir are initially uncorrelated, such that our reservoir essentially holds no initial information about our system. So if we want to measure the reservoir, we can't learn anything about the system if we assume that this assumption is true. And so this could occur in situations where, for example, our system and reservoir are initially uncoupled to each other, and then at some time that we call t equals to 0, we put them in contact with each other, and then they start to evolve under a time evolution that's described by this expression. And another important point to make out is that these Krauss operators obey the so-called completeness relation, and what this does is it ensures that our density matrix at some later time t is still has unit trace. So in other words, we still have appropriate normalization probabilities. Okay, and this kind of, so as I said, in this week's lecture, what I'll do is I'll kind of elaborate more on the concept of what in last week's lecture I call the dynamical map. So what you can do is kind of more abstractly kind of conceptualize time evolution through the framework of what's called quantum maps or dynamical maps. So in this week's lecture, I'll kind of go into much more detail about this idea. And then what we'll do is focus on a particular kind of class of dynamical maps, which are called dynamical semigroups, and then use this to formalize the idea of what's called a Markovian master equation. And then in the remainder of the lecture, kind of time to I'll look at how firstly, how we can phenomenologically motivate the idea of Markovian master equation, and then show how, starting from a microscopic model, so from this system reservoir model that I had on the previous slide, how we can derive these types of master equations from first principles, and then time permitting at the end, depending on how quickly I get through the material, I'll then show how within the framework of Markovian master equations, how you can construct this first and second laws. Okay, so as I kind of mentioned last week, we can, from this Krauss representation, we can kind of more formally think about time evolution of open quantum systems through what's called a dynamical map between states. So formally, what we can do is we can define a dynamical map, which is denoted by this phi t, as essentially a linear map from physical states of our system to other, or it represents a map between physical states of our system for any t, so here the t represents time parameter, which is greater than or equal to 0. So to kind of illustrate what I mean by a kind of dynamical map, in last week's lecture, I talked about how you can describe time evolution of an isolated system in terms of a unitary operator. So this unitary operator, this unitary time evolution operator, essentially represents a linear map from a pure state at some initial time that we call t equals 0 to a state at a later time. And this is prescribed through the Schrödinger equation. So what we're doing here is we're kind of introducing a more kind of generalized notion of time evolution that applies not just to, that isn't just described through a single unitary operator, but can describe more general types of operations. And so essentially here, this dynamical map is kind of a generalization of this time evolution that's described by this unitary time evolution operator. So it represents a linear map from some kind of state, from a density matrix at initial time to a density matrix at a later time. And so yeah, you can also kind of show this more formally. So on the previous slides, I wrote down the Krauss representation of time evolution. So you can show more formally that the time evolution described by the dynamical map is a kind of generalization of unitary time evolution, in the sense that when you only have a single Krauss operator, so then maybe I can just go back to here. So in the case where you only have a single Krauss operator, you can kind of straightforwardly show that this time evolution just reduces to the standard unitary time evolution. And so that's because in the case where you only have a single Krauss operator, this kind of trace preservation condition just reduces to the standard unitary condition that you have with kind of isolated systems. So hopefully that kind of makes it somewhat clear that this dynamical map represents a more generalized notion of time evolution. So it can describe dynamics that are non-unitary. Okay, and so in order to kind of formalize this concept, what we can demand is that if we want to introduce a linear map that describes time evolution, then it has to fulfill a certain set of properties. And what these properties are intended to do is to ensure that if we take in some initial state at some time equal to 0 and evolve it through this map, then we always get a physical state at the end of this evolution. And so that imposes certain constraints this map has to satisfy. And so these constraints can be written in the following way. So obviously we require our map to be trace preserving. And so this can be written, so this is just written here. So this is just saying that the trace of the state that we get out of evolving our system under this map is just the same as the trace at the initial time. And so this is equivalent to normalization probabilities, essentially. So making sure they're normalized to 1. Okay, and then the other requirement is hermeticity. So, you know, all density matrices are Hermitian operators. And so again, if we evolve rho under this map, what we get out again has to be a Hermitian operator. And the last requirement that we need is what's referred to as complete positivity. So, so as you can recall, density matrices are positive operators or positive semi-definite matrices. And what this complete positivity requirement does is essentially conserves this property of the density matrix. Although I should emphasize that the constraint of complete positivity is stronger than the requirement of only positivity. So positive maps are those which essentially map positive operators into other positive operators. Completely positive maps are slightly more, or this constraint of complete positivity attributed to them or associated with the map enforces a slightly stronger requirement. And so this can be summarized in the following way. So what we're saying is what formally complete positivity is derived or is stated in the following way. So it says that if we take our map phi and we tensor it with an identity map that acts on some kind of ancilla space of dimension k, then our density matrix that belongs to this dilator space has to be positive or non-negative. And so I appreciate this is maybe not kind of conceptually clear, but or conceptually obvious, but let me just say that so complete positivity represents a kind of stronger version of positivity in the sense that in the special case where k is equal to 1, then this just reduces to the statement of positivity, i.e. if we evolve rho according to phi, then we should get another positive operator out. And so to kind of intuitively explain why we need, what you could say, why do we need complete positivity over just positivity? And essentially the explanation of that is that if you're dealing with composite systems, say you can think of maybe an example of if you have two spin half systems. If we take a composite system of this kind and evolve it under a linear map phi, it's plausible in a situation that we could construct a positive map such that the state of our two spin half system that we get at the end is a valid density operator for our composite system. But it turns out that if you only consider positivity, not complete positivity, you can get the situation where the density matrix corresponding to one of the marginal states of the system, so of just one of the spin half systems, can potentially produce things like negative probabilities. So in other words, this complete positivity requirement is necessary to stop this type of unphysical situation from happening. Okay, so just these are the kind of the three things that we require of our map phi in order to describe physically time evolution in open systems. And so it turns out that that there's a kind of very useful theorem that tells us that so this is a theorem attributed to Krauss that essentially states that any linear completely positive and trace, given a linear completely positive trace preserving map phi, there exists a set of Krauss operators, which are denoted by these Ks, such that this map phi can be written in this so-called Krauss representation that I introduced last time. And so as before, these Krauss operators satisfy this completeness requirement. So just to clarify here, so a completely positive and trace preserving map, or what I'll call a CPTP map, is any map which satisfies these three requirements. And so what Krauss's theorem tells us is that if we're given a phi which satisfies these requirements, then we can always construct this map in the following Krauss representation, where these Ks are just any kind of linear bounded operators that apply to our system. But also the power of this theorem is that it's bidirectional. So it tells us that not only, if we're given a CPT map, that it will automatically, then we can always write in this form, the inverse holds as well. So in other words, if we have any kind of time evolutional operation which can be written in this Krauss representation, then the corresponding map will always is guaranteed to satisfy these requirements. And so that's important in the context of time evolution, because let me just go back quickly. So the time evolution that I showed here that's written in this Krauss representation can always be, under this separability condition, can always be represented in terms of a CPTP map according to this Krauss theorem. And that's useful because that tells us that if we evolve an open system non-unitarily in this way, then we're always guaranteed to physically get given back, we're always guaranteed to get back a reduced density matrix that is that represents a physical state of our system. So a density matrix that is that has unit trace, that is positive, and that is Hermitian. Okay, so this Krauss theorem is quite important in conceptualizing time evolution in an open setting. And so, okay, having introduced this, well, I should say that what this theorem allows us to do is describe the time evolution of open quantum systems in terms of CPTP maps. And so what we can do now is focus on a kind of specific class of CPT maps that are connected to what are called Markovian time evolutions. So I'll elaborate a little bit more on that in the next few slides. So we can say, okay, so yes, as I stated, so an open system dynamics can in general be described by what's called a family of one parameter CPTP maps. So these are essentially a collection of completely positive and trace preserving maps that depend on this parameter t, which is interpreted as a time parameter. And so obviously at t equals to 0, this just corresponds to the initial condition. So our map at t is equal to 0 is just given as the identity operation. So an operation that doesn't do anything when applied to our system. Okay, so what we can do is now focus on a kind of a subclass of a special subclass of these one parameter CPTP maps. And so these are ones which are called or which obey a so-called semi-group property. So a dynamical semi-group can be defined in the following way. So it's any map that basically satisfies this property. So this kind of operation represented by the circle here represents the composition of these two maps. And this applies to, so essentially what this is saying is that any phi can be broken down into the composition of two other maps which belong to the same one parameter family. And this has to apply for any t and s greater than or equal to 0. And so I'll talk about how this is kind of connected to the conceptualization of Markovian time evolution. But before I do that, I can say that, let me just say that you can think of this kind of semi-group property of a maps as being kind of the quantum analog of what's called a Chapman-Kolmogorov equation. So for those of you who are kind of familiar with classical stochastic classical stochastic evolutions, what the Chapman-Kolmogorov equation is essentially it's a equation that can be used to characterize what are called random processes, that are called Markovian random processes. So yeah, so this is just important to note that when I go on to introduce the idea of Markovian dynamics and Markovian time evolution for open quantum systems. So essentially, a Markovian evolution is one which is memoryless. So it's a kind of random process that has no where it's a random process where the state of the system at a particular time has no memory of its history, in a sense. Okay, and so having introduced this semi-group property, what we can do is we can know that under certain conditions we can write CP-TP maps that are dynamical semigroups in the following way, where this kind of calligraphic L operator here is what's called the generator of the map, and so that can be constructed in terms of like the limit of this limit that's represented here. And so this L is called the generator of the map. Is sometimes in the literature also referred to as the Liouvillean, and hence why the calligraphic L notation. And so I said under certain conditions we can write this. So in the next slide I'll talk about what these conditions are. And so okay, with this form of the dynamical semigroup, we can write down the our reduced density operator at some particular time will just be given as the in terms of our map phi acting on the initial state, so rho s 0. And so if we just take the time derivative of this expression, then what this does is it shows that we can write we can construct our time evolution in a kind of differential form where we have this differential equation, which is d dt of rho st is equal to L of rho st. And so this introduces the idea of what's called a master equation. So essentially a master equation is a first order differential equation for the reduced density matrix of our system that essentially tells us how our open system evolves in time under the action of a CP-TP map. Okay, so I said under certain conditions, CPT maps that obey a semi-group condition can be written in this form. So okay, what are these conditions? So these there's a kind of a couple of seminal results in the theory of open quantum systems. So which are attributed to Guarini, Kosakowski, Schudershan, and Lindblad. And so what they did is they essentially came up with these theorems that gave us the most general form of the generator, so L of a dynamical semigroup under a certain set of conditions. So basically, there's this kind of important theorem in open systems theory which is called the GKSL theorem that basically states that if we have a dynamical semigroup in this form, the most general form of this generator can be expressed in for a finite dimensional system or open system of dimension d, then it can always be the generator can always be expressed in this form. So so in this expression, so let me just kind of introduce a few things here. So in this expression, we have this first term that depends on what's formally just a self-adjoint operator, which I call H0. But you can think of it as kind of a Hamiltonian. And then we have this kind of second term that depends on these parameters, what labeled as gamma k. And so kind of intuitively, or kind of from a more physical point of view, you can think of these rates as formally they're just positive parameters, but physically you can think of these as representing so-called transition rates. So I'll kind of elaborate a bit more on this as we go through the next couple of slides. And there are these additional kind of operators in this expression which are labeled as VK, and these are just in general, these are just any linear bounded operators acting on our system. And these are what are sometimes called Lindblad operators. So physically, what they kind of represent for maps of this type, what they can physically represent are the different possible transitions that can occur between the, say, energy levels of our system. And so this is this kind of master. So as I introduced on the previous slide, master equation is essentially just a differential equation for the reduced density matrix of our system. And so master equations that can be written in this particular form are what I've referred to as Markovian master equations, or more specifically, they're referred to as Markovian master equations in so-called GKSL form. And so these represent a kind of very special class of master equations, mainly for the reason that the dynamics that they described always describes what's called a completely impositive trace preserving dynamic. So in other words, the corresponding time evolution that this type of master equation describes is that which is given by CPTP maps in this kind of form. And as I kind of mentioned, these maps always give us, always describe a physical time evolution in the sense that they always take a state at some time, evolve it to another state at a later time, which is can be represented as a reduced density matrix. Okay, so this is a kind of seminal result, as I mentioned, of Guarini, Kosakowski, Schudersan, and Lindblad. So I think that originally, this theorem was proven in the finite dimensional case by Guarini, Kosakowski, Schudersan, and then Lindblad generalized this to the case of infinite dimensional systems. And as far as I'm aware, so this also only applies to cases in which you're dealing with, in which these operators here are represented by bounded operators. So I think, as far as I'm aware, the case for unbounded operators is still an open question. Okay, so this kind of mathematically just gives us a particular structure for the generator of our map, which is a dynamical semigroup. So to kind of give more physical or to kind of go into more detail about the physical intuition behind this type of behind these types of master equations is that we consider just like an explicit example. So let's just say, okay, say that we have like a two-level system. So essentially it's just a quantum system that can either be in one of two states, which we label as 0 and 1. And so formally this corresponds to a state space which is written as the span of what I call here as 0 and 1. So you can think of 0 as representing the ground state energy of our system, and state 1 as representing the excited state of our system. So if we put energy into our system, what happens is that it can move from its ground state to its excited state, and potentially also the system can lose energy and move from its excited state to its ground state. And so if we just define these operators in the following way, so we say what's called the Pauli Z operator as the following, and we can also introduce these raising and lowering operators in this way, then an example of a Markovian master equation is one which is given here in this block. And so where this parameter omega naught here gives us the energy difference between these two states 0 and 1. And so a particular type of situation that this type of master, so here we just introduced this master equation phenomenologically based on this so-called GKSL theorem. So it's a Markovian master equation that describes the dynamics of a two-level system, which has which can exist in either two of energy states. And so kind of physically, what does this equation actually describe? And so physically, what it does is it essentially can describe the damping of our system under the action of a of a bosonic reservoir. So what you can do is you can kind of, starting from first principles, you can derive master equations of this type, and this is something that I'll go on into in the remainder of this lecture. But what this type of master equation describes is the dynamics of a two-level system that spontaneously emits photons at a particular rate, which is measured by gamma. So what gamma does in this equation tells us this, that if our system is in the excited state, then it will lose some quanta of energy, omega naught, at a rate gamma. And so just to emphasize here, so this H naught for this example is just given as omega naught over 2 times by this Pauli Z operator. So here it's clear to see that this is just a Hermitian operator. And in this case, this is just the Hamiltonian of our two-level system. So it's just the Hamiltonian that describes the energy states of our system in absence of its interaction with the reservoir. Okay, so hopefully that's kind of somewhat intuitively kind of clear what these kind of Markovian master equations describe. And so, so for the remainder of this lecture, what I'll do is talk about how starting from a paradigmatic system, a reservoir model, so the type that we encountered previously, how we can actually derive master equations that are in this particular GKS cell form, and also the assumptions that we generally have to make in order to derive these types of equations. So just to reiterate, so the equation, the Markovian master equation that I just gave was kind of phenomenologically motivated based on the GKS theorem that restricts the form of the generator corresponding to dynamical semigroups. So now what we want to do is say, okay, let's just consider a different situation now. So we're not looking at a phenomenological situation now, we're looking at a particular microscopic model where we have an open system that interacts with a thermal reservoir, and the total Hamiltonian of our system plus reservoir can be in general written in the following form. And so here H of S is just the Hamiltonian of our system, HR is the Hamiltonian of our reservoir, and then this last term is a term that describes it encodes the interaction that occurs between the system and reservoir. And so in general, this will just be some kind of self-adjoint operator. So here we're just considering a generic case where we're not specifying any particular interaction. But what we can do is say, okay, because this is a self-adjoint operator, in general, it can be written as the sum of operators belonging to just the open system, or self-adjoint operators just belonging to the open system, and also self-adjoint operators that just belong to the reservoir. So here, just to emphasize that these AK are self-adjoint operators belonging to the system, and these BK are self-adjoint operators belonging to the reservoir. And so this just, as I said, represents a general decomposition. And this alpha, what this alpha parameter does, it's just an additional parameter that characterizes the strength of the interaction between the system and reservoir. So, I'll talk a bit more about that. So in this kind of setup, what we want to do is to derive, to show that we can derive Markovian master equations for the reduced density matrix of our system, assuming that it undergoes a time evolution that's described by a CPTP map. Okay, and so these are some kind of generic assumptions that if we want to do this, we have to kind of make a sequence of assumptions or restrictions on our model. And these are and so here I'm just going to state what some of these restrictions are. And so obviously, I should mention first that the one that we introduced at the beginning was this separability criteria. And so here we're also assuming the same thing. So we assume that our open system and our reservoir initially start in this separable state. Okay, and so some additional ingredients that we need are the fact that we assume that that our system and our reservoir only weakly interact with each other. And this is equivalent to from this formula, this is equivalent to saying that this parameter alpha that characterizes the interaction strength is generally much less than 1. So we assume it to be very, very small. And so this is also, so this kind of weak coupling assumption between the system and reservoir is also sometimes what's referred to as Born approximation. So more formally, what the Born approximation is it's a statement based on the weak coupling assumption. What it says is that the global density matrix of our system and reservoir approximately at all times can be written in this separable form. And so just to point out that this is qualitatively different from the assumption of initial separability. So this is saying that not just at the initial time, but approximately at all times we can assume this factorization to hold. And this is kind of, I should point out is that strictly speaking, this is never actually true. So hence I use this approximation sign because strictly speaking, if our system and reservoir interact with each other, there's always going to be some correlations that build up between our system and reservoir. So strictly speaking, this is never 100% true, but it's kind of an idealized assumption that we can make in order to construct our Markovian master equation. And so how this relates to weak coupling is that, well, in the case where there's only weak interactions between the system and reservoir, what happens is that as our system and reservoir interact, the state of our system is going to change with time, but also the state of our reservoir is going to change in time due to its response to this interaction. But what we're kind of saying with this weak coupling assumption is that because our reservoir is so large, it's macroscopic compared to our system, is that if we assume that it starts in equilibrium, so which I'll mention just below, if it starts in a thermal state, so it's initially in thermal equilibrium, under this weak coupling assumption, we assume that at all times our reservoir more or less stayed in equilibrium. So it just remains, for the timescales that we're interested in, the state of our reservoir approximately doesn't change in time. Which, okay, if there are strong interactions, you can think of, you know, if we drop this assumption and say that these two strongly interact, you can think that, okay, the reservoir is not going to remain static. Its state is going to significantly change in time. Okay, so the other thing that we also assume is that, so in the context of thermodynamics, obviously the kind of the basic setup that we consider in thermodynamics is a system that's placed in contact with a thermal reservoir. And so we assume that the initial state of our reservoir is can be represented in this way. So at the end of the last lecture, I kind of introduced the notion of the Gibbs state. So the Gibbs state is a particular state which maximizes the von Neumann entropy at particular fixed temperature. So here beta is the so-called inverse temperature parameter that you may recall from last lecture. So this is just equal to 1 over kBT, where kB is the Boltzmann constant, and this Z is the partition function. So this state here is equivalent to essentially the canonical ensemble from statistical mechanics. Okay, and another kind of, it's not really an assumption, but it's another important thing to mention is that something which relates to the system and reservoir energy is what we also do is say that this particular relationship holds such. So here we're assuming that the expectation value of these reservoir operators that appear in the decomposition of the interaction Hamiltonian satisfy this relationship. And so this is an assumption. I won't go into the details of this. This is an assumption. We can always make sure this is true by appropriately redefining our Hamiltonian or just adding and subtracting additional terms to our Hamiltonian. So this is an assumption, but the reason why it's important to mention is because if this is true, then we can show that the expectation value of our global Hamiltonian, which represents the energy of both the system and reservoir, can be written as just the contribution of the system energy plus the reservoir energy. And this is important when we go on to talk about the first law. So I won't mention it much here, but when we go on to talk about the first law, this becomes important. Okay, so with this model and with these assumptions in place, what we now want to do is go on to show that we can derive an equation of motion for the reduced density matrix of our open system, which can be written in the form, a particular GKSL form. So which can be, in other words, written as a Markovian master equation. Okay, so how do we do this? So what we do is we start and say, okay, well, because our global system, so our system plus reservoir, it's an isolated system, so therefore it just evolves according to the Liouville von Neumann equation. So this is, again, I introduced this in the previous lecture. And before, what we do here is we also transform to what's called the interaction picture. So again, I won't go over the technical details of this, but just to clarify here, these operators, so the density matrix here and these operators that have these tildes on them. So this tilde notation indicates that this is defined in the interaction picture. And here, this V term is just shorthand for, so this represents the interaction Hamiltonian of our system in the interaction picture. So this is decomposed in terms of these A and B operators in this way. And so this describes the time evolution of our system plus reservoir. We can formally integrate this to get the following. What we can then do is substitute this kind of formal solution back into this equation and then take the partial trace of both sides to get an equation of motion for just the reduced density matrix of our system. Okay, and so by doing so, and also if we make use of the Born approximation that I gave on the previous slide, so if you recall, the Born approximation says that the density matrix, the global density matrix of time t, can be factorized into just the density matrix, the reduced system density matrix at the same time, and also the canonical distribution of our reservoir. So we basically, with the Born weak coupling approximation, we get this equation of motion. And so now what we want to do is evaluate this partial trace that is taken over these terms in the integrand. And so just to point out here, so our integrand here is written as a double commutator. So I think there's a slight mistype. So there should be an additional bracket at the end of this expression. So what we have inside this integral is a partial trace over a double commutator. Okay, and what we've also done in this expression is that you should also get an extra term that depends on the initial condition or rho at t is equal to 0. But what we can do is show that with this additional property that I kind of mentioned on the previous slide, is that this extra term vanishes. And just to re-emphasize that we can always make sure that this property holds. Okay, so with the weak coupling assumption, we have this equation of motion. So what we can do now is, what we at least want to show is that we can write this equation in making use of some additional assumptions. We can write this equation in the form of a Markovian master equation, so in a particular GKSL form. Okay, so what we do now is we say introduce some kind of what are called timescales. So we say let this tau I and tau R denote interaction and reservoir timescales. So what these timescales basically tell us is, or give us an indication of the rate, or their inverse gives us an indication of the rate at which our open system evolves due to its interaction with the reservoir. And what this tau R does is it gives us an indication of how quickly our reservoir evolves also under this system reservoir interaction. And so what we do is we say, okay, we can introduce a kind of Markov approximation by saying we assume that there's a large separation between these timescales. So we say that we assume that the timescales that determine how quickly our reservoir evolves are much smaller than the time, or is much smaller than the timescale that determines how quickly our open system evolves due to the interaction. Okay, so if we make this kind of so-called separation of timescales argument, then what we can do is we can make kind of two modifications of this equation at the top of the slide. So what we do is we do the following. So what we say is that, okay, if our system, our open system, evolves much more slowly than our reservoir, then in this integrand, we can expect the reduced density matrix of our system to only vary only marginally with respect to terms on the right hand side here that depend on this timescale TR. So based on that statement, what we can do is say, okay, we can replace the density matrix here that depends on all previous times. So here we kind of have a kind of so-called kind of time retarded expression. So our reduced system density matrix here doesn't just depend on the kind of present time. It depends on all previous times that are indicated by this parameter s. And so what we're doing here is saying, okay, if we assume this evolves very slowly in comparison to the reservoir terms that are also contained in this integrand, then we can just replace rho s here by its current time. And so this is kind of relates to the idea of a Markovian time evolution. So if you recall, previously I said that a Markovian random process is one which contains no kind of memory of its history. And so in other words, it's a kind of memoryless kind of random process. And so we're kind of invoking that kind of idea here. We're saying that based on this separation of timescales argument, we're saying that our system, the state of our system at some current time is independent, approximately independent of its history. Okay. And so that's one modification that we do. A separate modification that we make is that we extend the time limit of the integral to infinity. So this is also based on this separation of timescale. And the reason that this is justified is because we're essentially saying that the integrand decays fast enough such that if we extend our t limit to infinity, then we're only very marginally changing the value of our integral. So yeah, in other words, fast decaying integrand. Okay, so what we've done is we've used the weak coupling approximation, and we've also introduced this Markov approximation, which is based on separation of timescales. And so now what we can do is, having made these approximations, what we can now do is substitute in an explicit expression for this interaction Hamiltonian in the interaction picture. And so generally what you can do is decompose this interaction Hamiltonian in the following way in terms of what are called eigenoperators of the system. And so I'll explain a little bit more about what those are. But if you basically do this and you just substitute that into the expression on the previous slide, you get this master equation. So this essentially what this is now is an equation for our reduced density matrix that it's a Markovian master equation because it relies on these the Markov approximations that I introduced in the previous slide, but it's not as of yet in GKSL form. Okay. And so, okay, what are these eigenoperators? So basically, we can define a set of eigenoperators of our system. These are basically operators that obey this kind of eigenvalue relation here. And so what this parameter omega is it's a parameter that basically it's a label that basically runs over all energy differences in the energy levels of our system. And so again, I'm kind of skipping over a few technical details here, but basically what this if we introduce these eigenoperators, what we can basically say is that these system operators, these self-adjoint system operators in the interaction picture can always be written in the following way. And so what you can demonstrate is that with this definition is that if you transform to the interaction picture, you can extract this time dependence in the form of e to the minus I omega t. And that's useful when we make in the next slide, I'll introduce another approximation, which is a so-called secular approximation. And so to make this approximation, we have to perform this kind of decomposition. And so what I've also introduced in this equation up here is these kind of quantities, which here I call gamma KL, which also depend on these energy differences omega. So this quantity here is sometimes what's referred to as the spectral density or the reservoir spectral density. And these are formally, and so this is formally defined as in terms of this integral. So you can show that this is equal to the Fourier transform of this quantity, this time-dependent quantity, which is known as the reservoir correlation function. So this essentially is a time-dependent function, which is in the form of a correlation function. So it's basically the expectation value of these reservoir operators with or a two-time expectation value essentially of these reservoir operators, where one of the time arguments is just set to 0. And just to note here that this notation, this kind of subscript beta notation, indicates that this is an expectation value that's taken with respect to the thermal state of our reservoir. Okay. So I should also point out here is that if you go through this derivation step by step, you also introduce what's called a Lamb shift term. Here, just for the sake of simplicity, I've ignored this from the derivation. So, which is justified on the fact that it's generally in kind of practical applications, it's usually only a small addition to the master equation. So, just to emphasize here that generally you get an additional Lamb shift, which here I assume to be 0. Okay, and so I kind of mentioned that we want to make, so far we've made the Born approximation, which amounts to weak coupling. We made the Markov approximation, which amounts to separation of timescales, or assuming our system has a memoryless evolution. And now we introduce this one last approximation, which is called the secular approximation. And so this is another approximation which kind of relates on the separation of timescales argument. So, okay, this equation here is just the one I gave on the previous slide. And to make the secular approximation, what we do is for terms, so for terms which depend on these energy differences, omega and omega prime, what we do is we neglect all terms that for which omega prime and omega are not the same. So essentially what we do is we just set omega prime and omega are equal in this expression. And so this is kind of justified under the following. So what we do is we say, okay, we introduce another time scale, which we label as tau s, and we denote this as a system time scale. So essentially it's another type of time scale that tells us how quickly our open system evolves in the special case in which our system and reservoir are non-interacting. So this kind of determines what's called the times, it determines how quickly the free evolution of our system happens. So when I say free evolution, I mean the evolution that happens when essentially the interaction between the system and reservoir is completely switched off. Okay, and so if we basically assume that this kind of free evolution, it happens much quicker than the evolution over which, or the evolution determining the response of our open system due to the interaction, then what we can do is neglect these the terms for which omega prime is not omega. So this is the secular approximation that I mentioned, and the result of that is that we get the final result is that we basically get an equation of motion for the reduced density matrix of our system, which is in the form of a GKSL master equation. So it's a Markovian master equation in GKSL form. And so if you recall from the previous slides, I gave the kind of the generic construction for the generator for a Markovian master equation, and you can kind of confirm here that this master equation is in fact in this kind of GKSL form. So just to kind of reiterate, the requirements for that is that this operator that appears here is self-adjoint, which, okay, you can see that this is the system Hamiltonian, so by definition it's a self-adjoint operator. And these AL omegas are bounded operators, linear bounded operators of our system. And the final requirement that we need for this to be in GKSL form is that these coefficients are positive. And what you can do is show, in fact, that so these form the coefficients of essentially a matrix. And you can show that this matrix is a positive semi-definite matrix. So this relates to something that's called Bochner's theorem, but I'm not going to go into details about that. Okay, so I should also just finally actually mention, so what I've done in this last step is also transform the secular approximation. You transform back into the Schrodinger picture. So this equation is written in the Schrodinger picture. And so, yeah, so just to kind of summarize all the approximations that we made in order to derive a Markovian master equation. So we made the Born approximation, which amounts to the assumption of weak coupling. So that's basically what we did, is say, okay, the global density matrix of our system and reservoir can always be factorized in this way. So in other words, kind of physically, our reservoir remains approximately, whilst our open system will generally evolve, its state will evolve in time. Our reservoir, on the other hand, its state will approximately remain the same. So it will remain static under under time evolution. Okay, what we also made is the Markov approximation. So this was an assumption relating to separation of timescales. So what we did is say that the timescale that sets the evolution of our reservoir, or more formally, this tells us how quickly the reservoir correlation functions decay. What we said is that these reservoir correlation functions decay much faster than the timescale over which our open system evolves due to the interaction. Okay, and then the final approximation that we made, which is also based on timescales, was the secular approximation. So this is, I should also say that the secular approximation is also sometimes called the rotating wave approximation in the literature. And so this related to saying that the free evolution of our system happens much faster, or at least on a much faster timescale than the evolution due to the interaction. Okay. So that kind of finalizes this kind of the microscopic derivation of the Markovian master equation. And so now I'm not sure if it's worth, because at the end of this lecture I had sections on how you can derive the first and second law, but I don't know if it's worthwhile to continue or to relegate this to next lecture. Maybe I can just quickly go over this, and then in next lecture I can recover this material. So in case I go over it too quickly, then I can just I can go over this again. So hopefully I should be able to finish in, so I apologize for already going over time, but hopefully I should be able to finish in 5 minutes or so. Okay, so we have now this kind of microscopically derived Markovian master equation. And so what we can do is we can study what are its kind of, what does it tell us about the asymptotic behavior of our system? So if we have an open system that evolves according to this equation, what is its state? What state is it in after a very long time? So as it approaches its what's called a steady state. And so under what's called the kind of KMS condition, or Kubo-Martin-Schwinger condition, which is stated in the following way. So this is a kind of condition that's attached to the reservoir correlation functions of our reservoir. And so I won't, again, formally I won't go into this, but essentially it's the KMS condition states this relationship. And so if this is, and so you can in fact show that for generically for reservoirs which are in thermal equilibrium, so whose state is given by the Gibbs state, then generally speaking this relationship holds. So thermal states obey this so-called KMS condition. And so if this KMS condition holds, what one can show is that the fixed point of the generator of the underlying map is a thermal state. And this, and so yeah, the thermal state here, so this is the thermal state of our system. So the Gibbs state of the system is the fixed point of this generator. So this is just here, I've just written down what the Gibbs state is for our system. So it depends just on the Hamiltonian of our system. and also the temperature of our reservoir, or the inverse temperature of our reservoir beta. And so basically what this is saying is that with this, if this KMS condition holds, then the Gibbs state of our system is a unique stationary state of the underlying map with this generator. And what this implies is that if we start our system in any state and evolve it in time according to this master equation, then if we wait a sufficiently long time, so formally as t goes to infinity, our system will always evolve into a Gibbs state at the bath temperature. So kind of physically, this is kind of quite intuitive, because this is just telling us that our system eventually equilibrates with the bath or with the reservoir at the reservoir temperature, which is what you would expect in the case of weak system reservoir interactions. So this is what you would expect from kind of standard macroscopic thermodynamics. Okay, so actually, no, maybe it would be a better idea to just leave this material for next week's lecture, because I think we've already covered enough for now, and also I realize that it's already quite far over time, and there's also questions as well. So so I apologize if I skip over this material, but I will. So what I'll do is in the next few slides, what I'll do is go on to show how we can formulate the first and second laws of thermodynamics within the framework of Markovian master equations. And so, yeah, it's essentially applying what we've introduced in this lecture to derive the first and second laws. So because I don't want to go over this material too quickly, I will defer this to next week's lecture, I think. So yes, so hopefully, so apologies for that, but hopefully, yeah, I would prefer to go over things thoroughly rather than quickly have to skip over any of the material. Okay, so just to then finalize and finish up. So what we did was in this lecture, what we did was formalize the open system dynamics in terms of what are called completely positive and trace preserving maps. Okay, and so for the class of completely positive and trace preserving maps, obeying what I call the semigroup property, then we can show that we can introduce the generic construction of a Markovian master equation, which is essentially first order differential equation for the reduced density matrix of our system. And in general, this can be written in, so for CPT maps which are in a semigroup form, this can in general be written in this so-called Guarini-Kosakowski Sudarshan-Lindblad form. Okay, and then what we did in the remainder of the lectures, we just outlined a microscopic derivation of such master equations. So starting from a system reservoir model, how we can introduce a kind of a set of physically motivated approximations that that allow us to kind of derive an equation of, derive a Markovian master equation for our system. And then what I will do in the beginning of next week's lecture is show that within this framework of Markovian master equations, how we can derive the first and second laws of thermodynamics. And also then what we'll go on to do is look at applications of this framework to thermal machines. So I will focus on a particular example of a thermodynamic cycle, which is known as a quantum Otto cycle. Okay, so yes, apologies for going over time. So let me just finish by saying thank you, and also kind of shamelessly promote our group. So this is the website of the quantum the quantum research group here at Stellenbosch. If you're interested in more of the work that we do, then please feel free to check out our webpage. So okay, let me finish there by saying thank you.
Okay, yeah, Graeme, thank you very much for the very nice introduction. And